Hello friends, I am Rahul Hinge. Welcome you all to the second part of first unit of process calculation. So far in first part of the first unit, that is mathematical principles, we have covered the unit operations and unit processes, their classification, steady state and unsteady state, then units and dimensions, different ways of expressing the units, and also we have covered the convergence of units. Now, in the second part, the content is first the ideal gas law, that is the concept of ideal gas, the formula for ideal gas, then basic chemical calculations. What are the various ways of expressing the composition of mixtures and solutions? And lastly, the mole fractions and partial pressures. Let's start then. The first topic is ideal gas law. On the rough experimental knowledge, it has been proven that there is a specific relationship between pressure, volume, and temperature at a moderate condition of temperature and pressure. We get the equation applicable for ideal gas, that is PV is equal to RT, wherein P is absolute pressure, V is molar volume, R is a universal constant, T is absolute temperature. Or it may be written as PV is equal to nRT, wherein P is absolute pressure, V is volume in meter cube, N is number of moles, R is a universal constant, and T is absolute temperature. The difference between two equations are, for the first case, it is a molar volume. It means it is having a unit meter cube per mole, so that there is no term of moles in first equation, because V stands for molar volume having unit meter cube per mole. And in second equation, the molar volume is separated in the terms as V for meter cube volume in meter cube, and N is the number of moles. Okay, so in both ways we can give the statement of ideal gas. Okay, and for the standard condition of temperature, that is 273.15 Kelvin, and pressure 1 atmosphere, the volume of 1 kgmole of gas is 22.414 meter cube. This is the standard condition of temperature, pressure, and we can get the volume of 1 kgmole of gas as 22.414 meter cube. By using these values in ideal gas equation, we get the numerical value of R. As you can see, there are various numerical values of R with a respective units. Okay, if we convert, say, pressure 1 atmosphere into other units like bar, Pascal, Joule, we will get the various numerical values of R with respective units. So, while solving the problem based on ideal gas law, we have to find out the one unknown amongst this pressure, volume, number of moles or temperature. There we have to choose the appropriate R, which is totally depend on the units of pressure, volume, temperature and number of moles. If we want to use a numerical value of R as 8.31451, then the unit of that R is meter cube kilopascal per kilomole Kelvin. This suggests that while using this value of R as 8.31451, our volume must be in meter cube. Our pressure must be in kilopascal. N, that is number of moles, must be in kilomole and temperature must be in Kelvin. So in this way we can use the numerical value of R to find out the unknown amongst the pressure, volume, number of moles and temperature. Okay, no doubt we are going to cover some numericals in next presentation. Let's move forward. The next topic is basic chemical calculations. Okay, so before dealing with the material and energy balance of a process, we must be familiar with the basic principles such as molar concept, stoichiometric relations, various methods of expressing the composition of the system, then pressure, volume, temperature relationship of a gaseous system, etc. And factors to be considered while dealing with the calculations are: we have to check what data are provided, then what required answer is called for, then what is the relationship between the data and required answer, then what should be the most convenient basis to use, what should be the base of that numerical. We must consider appropriate basis of calculation. Let's move forward. The first term in stoichiometry or process calculation is atomic weight. The atomic weight of an element is the mass of the atom of this element based on the scale that assigns carbon a mass of exactly 12, and molecular weight, the molecular weight of compound is the sum of the atomic weights of atoms that constitute a molecule of a compound. It means atomic weight is applicable for an element and molecular weight is applicable for a compound. So, if Na is a element, we can treat Na as element while NaOH is a compound. Okay. Secondly, the molecular weight of a monoatomic element, that is for example sodium, is its atomic weight, and the molecular weight of a diatomic element, for example oxygen, chlorine, is twice that of its atomic weight. So, values of a molecular weight are built up from the values of atomic weights based on the scale of the relative mass of the element. The value 12 is selected in this case because an atom of carbon contains 6 protons and 6 neutrons for a total molecular weight of 12 for carbon. So, the scale of atomic weight, hydrogen is 1, carbon is 12, and so on. So, in this way, if we want to find out the molecular weight of a compound from the atomic weight of elements involved in the formation of that compound. For example, if you want to find out the molecular weight of NaOH, it is calculated as for Na as it appears once in that compound, that's why 1 into atomic weight of Na 23 plus 1 for oxygen as it appears 1 once in that compound into atomic weight of oxygen, that is 16, plus 1 stands for hydrogen element appears once in that compound into atomic weight of hydrogen, that is 1. Incorporating all, we get the molecular weight of NaOH as 40. Okay, where 23, 16 and 1 are the atomic weights of Na, O and H respectively. In this way, the atomic weight is applicable for a single element, while the molecular weight is applicable for a compound, which is made up from elements involved. So, one important calculation at which you should become skilled is to convert the number of moles to mass and the mass to moles. Okay. Now, what a special emphasis is given on this in process calculation, because we know that every chemical reaction say, now suppose the reaction H2 plus 1 half O2 gives H2O. This is called as balanced chemical reaction, which is read as 1 mole of H2 if reacted with half mole of O2, we get 1 mole of H2O. So, the reactions are carried out on mole basis. All the reactions in chemical engineering are carried out on mole basis, but the raw material available in the market is either on weight or mass basis or on volume basis. So that it is important to know the specific relationship between the mole and the weight or volume. So, the first term which relates the weight to the gram atom is a gram atom. So, the gram atom, it is used to specify the amounts of chemical elements. It is defined as the mass in grams of an element which is numerically equal to its atomic weight. So, the gram atoms of an element will be equal to weight in grams of that element divided by atomic weight of that element. Or if we are considering a special element A, then gram atoms of an element A will be equal to weight in grams of A divided by atomic weight of A. So, if we considered a 23 grams of Na, then if we want to find out the gram atoms of Na, it will be weight in grams of Na, that is 23 grams, divided by atomic weight of Na, that is 23. So, it will becomes 1 gram atoms of an element. Similarly, the mass in kilograms of a given element, that is numerically equal to its atomic weight, is called as kilogram atom. So, kilogram atom of element A will be equal to weight in kilogram of A divided by atomic weight of A. For the same case, if we considered a 23 kg of Na, 23 kilograms of Na, and we want to find out the kilogram atoms of Na, so we can put in this equation as weight in kilograms of Na will be 23 kilograms divided by atomic weight of Na, that is 23, it will become 1 kilogram atom of element. So, numerically 23 grams of Na will be equal to 1 gram atom of Na, and 23 kilograms of Na will be equal to 1 kilogram atoms of Na. So, for chemical compound, a mole is defined as the amount of substance equal to its molecular weight or formula weight. Now, the second term after gram atom is gram mole. It is used to specify the amounts of chemical compounds. It is defined as the mass in grams of a substance that is equal numerically to its molecular weight, and is given by gram moles of compound B will be equal to weight in grams of compound B divided by molecular weight of compound B. Now consider a compound NaOH, and if we take a 40 grams of NaOH and we want to find out gram moles of NaOH, then it will be weight in grams of NaOH, that is 40 grams, divided by molecular weight of NaOH, that is 40. It will becomes 1 gram mole of NaOH. So 1 gram mole of NaOH will be equal to 40 grams of NaOH. Similarly, a gram mole of a substance is the mass in grams of a substance that is numerically equal to its molecular weight. Okay, that's why 1 gram mole of NaOH will be equal to 40 grams of NaOH. Similarly, kilogram moles of compound B will be equal to weight in kilograms of compound B divided by molecular weight of compound B. Okay, if we considered 40 kilogram of NaOH and we want to find out the kilogram moles of NaOH, it will be weight in kilograms of NaOH, that is 40, divided by molecular weight of NaOH, that is 40, we get 1 kilogram moles of NaOH. So 1 kilogram moles of NaOH will be equal to 40 kilograms of NaOH. Okay, gram atom and gram mole are same, but gram atom is applicable for a element and gram mole is applicable for a compound. Okay, so for Na it will be gram atom, and for NaOH it will be gram mole. So a mole is defined as the amount of substance equal to its molecular weight. And next term is equivalent weight of an element or a compound. It is defined as the ratio of the atomic weight or molecular weight to its valency. Now what is the valency? The valency of an element or a compound is depends on the number of hydroxyl ion, that is OH minus, donated, or the hydrogen ions, that is H plus, accepted for each atomic weight or molecular weight. So the equivalent weight will be equal to molecular weight divided by valency. Okay, now what are the various methods of expressing the composition of mixtures and solutions? Okay, that may be a solid mixtures, gaseous mixture, liquid mixtures, or solutions. Okay, so the various methods are used to express the composition of mixtures and solution. Now we are considering the binary mixtures over here for the calculations. Binary mixture means two component mixtures, namely A and B, to generate the formulas. And the same methods are used for the system containing more than two compounds or more than two components. The composition of mixture or solution can be expressed. There are three different ways. Those are weight percent, volume percent, and mole percent. And we can use mole fraction and weight fractions also as the methods of expressing composition of mixture. Okay, so let's start with the first, weight percent or mass percent. It is the weight of any component expressed as a percentage of total weight of system. So weight percent of A will be equal to weight of A divided by total weight of system into 100. So WA upon W into 100. Here total weight of system, if we considered there is a two component A and B. Okay. So the total weight of system will be addition of the weight of both component A and B. Okay. So where WA will be weight of component A and W, that is total weight of system, will be WA plus WB will weight of component A plus weight of component B as far as binary system is concerned. Okay. So the weight percent of component A present in system is defined as the weight of the component A expressed as a percentage of total weight of system. Okay. The next is volume percent. Again, it is the pure component volume of any component expressed as a percentage of the total volume of system. So the volume percent of A will be equal to pure component volume of A divided by total volume of system into 100. So VA upon V into 100, where VA is a pure component volume of component A and V is the addition of pure component volume A and B for binary system. The third term is mole percent. It is the most important term for the calculations and process calculation. So mole percent, it is the moles of any component expressed as a percentage of the total moles of system. So for binary system A and B, mole percent of A will be equal to moles of A divided by total moles of system into 100. Now you know that moles of A will be equal to weight of A divided by molecular weight, so that it will become WA upon MA, where WA stands for weight in grams of component A divided by molecular weight of A divided by total moles of system. It is applicable for component A and B, that is moles of component A will be WA upon MA plus moles of component B will be WB upon MB into 100, where MA and MB are the molecular weights of component A and B respectively. Now the another way of expressing composition of mixtures and solution is mole fraction. Mole fraction, it is the ratio of number of moles of particular component present in the system to the total moles of system. Say for binary system of A and B, the mole fraction of A will be equal to moles of A divided by total moles of system. The mole fraction of A is given by small x subscript A. So XA is called as mole fraction of A and given by moles of A, that is WA upon MA divided by total moles of system, that is WA upon MA plus WB upon MB. Similarly, for component B, the mole fraction of B, that is XB, will be equal to MB upon WB divided by WA upon MA plus WA upon MB, that is total moles of system. So XA and XB will be mole fraction of A and B respectively. If we add mole fraction of A and B, we get XA plus XB will be equal to 1. So as the addition of mole percent is always equal to 100, addition of volume percent will be equal to 100 and summation of mass or weight percent will also be equal to 100. Similarly, the summation of mole fraction or weight fraction will be equal to 1. So, we can say that mole fraction will be equal to mole percent divided by 100, or mole percent will be equal to mole fraction into 100. So, the sum of the mole fraction of all components present in given system is equal to unity. Okay. In similarly, we can say that sum of the mole percent of all the components present in given system is equal to 100. ठीक है. Sum of mole percent, weight percent, mass percent, volume percent will be equal to 100. Similarly, sum of mole fraction, volume fraction, mass fraction will be equal to 1. So, we can say that the summation I is equal to 1 to n of xi, that is mole fraction of all component, will be equal to 1. The sum of all the mole percentage of a given system totals to 100. Now, the next term is weight fraction. It is the ratio of weight of the particular component present in the system to the total weight of system. For the binary system made up of component A and B, the weight fraction of A will be equal to weight of A divided by total weight of system. It is given again, x dash A will be equal to WA upon WA plus WB, that is total weight of system, where x dash A is a weight fraction of A. Similarly, for component B, x dash B will be equal to WB upon WA plus WB, that is weight of B divided by total weight of system. If we add x dash A plus x dash B, we will get it will be equal to 1. So, we can say that again the addition of weight fraction is always equal to 1, and we get a specific relationship, that is weight fraction will be equal to weight percent divided by 100. So, we can say that weight fraction of A will be equal to weight percent of A divided by 100, or weight percent of A will be equal to weight fraction of A into 100. The sum of the weight fractions of all components present in given system is equal to unity, or 1. So, we can say that summation component I is equal to 1 up to component number n. The summation of weight fraction of all component will be equal to 1. And similarly, we can say that the sum of the all weight percent for a given system is equals to 100. So, in today's session, we have covered the important basic chemical calculation, which includes first the ideal gas law concept. Okay, we have seen the statement of ideal gas law, the standard condition of temperature, pressure, and various values of gas constant R. After that, we covered some basic chemical calculations, starts from atomic weight, then we covered molecular weight. Remember, atomic weight is applicable for element, molecular weight is applicable for compound. Then gram atom, gram mole, or kilogram atom or kilogram mole. Again here, the gram atom is applicable for element, gram mole is applicable for compound. Then we covered equivalent weight. Then The last topic was various methods of expression the composition of mixture or solution. Those are weight or mass percent, volume percent, and mole percent. Weight percent is a ratio of weight of individual component divided by total weight of system. So weight percent of A will be equal to weight of A divided by total weight of system. Similarly, volume percent of A will be equal to volume of that element A divided by total volume of system. Similarly, mole percent of A will be equal to mole of that component A divided by total moles of system. Then keep in mind that the summation of all weight percent or volume percent or mole percent will be equal to 100. Then we covered the next method of expressing the composition of solution or mixture as mole fraction and weight fraction. Keep in mind that the summation of mole fraction is always equal to 1 and summation of weight fraction is also equal to 1. Okay, so these are some basic chemical calculations on which we plot a specific relationship between the various dimensions of, say, mass, volume, and mole. There is a specific relationship which is helpful to convert the given raw material, either it is on weight basis, we can convert it into volume percent, volume basis, or on mole basis. As I told you, the chemical reactions are carried out on mole basis, and normally the raw material available is on either weight basis or volume basis. So we must know the relationship between this volume, weight, and mole. So we have generated that relationship. In next presentation we will cover some numericals based on these 4 topics so that the concept will be clear. Thank you.